So I'm the next speaker, and I'm not going to introduce myself. So I'm going to talk about a synergistic project, so one that's been going on by EEMDL investigators, principally me and my collaborators, that is Project Astra. And so if we could pull up the slides for Project Astra. Project Astra, it will continue this theme of continuous monitoring systems. And what I'll do in describing what we've been doing for the last 3 years with Project Astra is describe how we went from just the problem of saying we want to deploy a continuous monitoring system all the way out to going and collecting data. How do you pick your sensors? How do you decide where to put them? How do you decide how many you need? I'll note that this project has been going on for 3 years. It's been funded by the organizations that you see on this list. I'll just name them off. Chevron, Environmental Defense Fund, ExxonMobil, GTI Energy, Microsoft, Pioneer, and SLB. And also the University of Texas not only receiving funds, but also directly injecting funds itself. And this Project Astra is now about to go into a phase 2 with some of the DOE funding that we've been hearing about. But let me tell you about our journey for the last 3 years or so. So the goal then was to do this in the Permian Basin. And what makes the Permian Basin interesting for continuous monitoring systems is several things. Number one is, for those of you who haven't been out to the Permian Basin, it's flat, all right? The wind blows. And so really great for getting you good plumes. And it's an important basin, as we've all heard, but then also the sites are extremely dense. And so what we wanted to probe here was, can we begin to design a multi-operator network? Right? Not having multiple sensors necessarily on each site, but to employ neighboring sites to give us information rather than having sensors north, south, east, and west on every single pad. So how efficient can we be in a multi-operator network? That was the fundamental question for Project Astra, and like many of the advanced technologies we've been hearing about, the goal was to go from relatively labor-intensive surveys using OGI and other techniques to sensors operating all the time, and then the necessary data analytics. So we went through 3 phases in this project. The first phase was, well, what sensors do we want to put out? And so we were doing this in 2020 and 2021, I'll point out. And the answer we might get today, we'll find out in the next phase with the Department of Energy. We'll go back and rethink our selection of sensors. But we asked the question, which sensors are ready to deploy right now in a network like this? Then we asked the question, if we take the types of models that Dorit just showed you, where would we put our sensors? How many do we need at each site? And so on. So we created digital twins, digital simulations of our sampling area. And then finally, we went out and built it, and we've been operating it since 2022. So the first question then was, all right, which sensors are ready? We went and surveyed the field in early 2020 and came up with 7 sensors that we thought we could deploy at roughly a 50-pad network at that point in time. And we tested them. They were all self-powered. They all had their own communications. And we tested them in a couple of ways. We went out and periodically challenged them with certified gases. And here we're just asking the question, not are they getting an emission rate right, but how well are they doing just measuring the concentration, all right, at the point at which they're making a measurement. And you see a trailer there that provided support. This was for a state-of-the-art sensor, a tilde sensor from Aerodyne that we use to directly compare to all of these sensors that we were considering deploying in the field. So a couple of different ways of evaluating it, and we wanted to know what precision and accuracy we could get. If we put these things out there in the field, what would be the data capture rate? And would the performance change over time? And so we tested for 9 months in the middle of COVID, from October 2020 to June of 2021. We compared these 7 sensors against the certified gas standards and against the TILDAS instrument that had a sensitivity of about, or a precision of 1 ppb at 1 hertz. What did we find? Well, we found that multiple sensors, at least for this criterion of are they getting the concentration right at the point that they're making the measurement, multiple sensors could get within about 10 ppb at 1 hertz. Right, these tended to be infrared-based sensors. The metal oxide semiconductor sensors, just in getting the concentration right, we're generally doing within about 500 ppb, maybe a ppm, changes in concentration at 1 minute resolution. What was the data capture rate? Generally better than 80% for most of these, even during what for the Permian Basin is extreme weather events. We have certainly very hot temperatures in the Permian Basin. We sampled through that, but we also had an extended freeze period during this, and many of the sensors did very well throughout those extremes. The big problem they had was dust, and you get a lot of dust in the Permian, but those were overcome over time. So based on that, we picked off 4 different types of sensors that we wanted to investigate further, 2 IR-based, and we eventually deployed 1 metal oxide semiconductor sensor system, and we made the decision to deploy those. But we first needed to address the question, where do we put them? How many do we need? And so to do that, we did digital simulations of all the sources on all the pads in our network, and basically said, how many sensors should we put out there? What precision do we need? Do we need a sensor that's going to be able to pick up a 1 ppm difference in concentration, 10 ppm? What threshold of emissions do we want to be able to detect? And so we wound up doing digital simulations. I'll show you another one of these videos. This is simulated data, not the actual data, but we did it for the actual sites. But I'm just going to show you simulations. So using the actual data, meteorological data from the Permian, here's a 10 kilogram an hour emission event from a single site, in this case represented by those little dots. And you can see from the colors where you're getting 1 ppm, 2 ppm enhancements. We also looked at episodic events. So what happens if we're only sampling these intermittent sources, so looking at once an hour? How many sensors would we need? And then we coupled that with all of the routine emissions, and what would we need in terms of precision and accuracy to see if we were putting a 10 kilogram an hour enhancement on top of all the routine emissions. So based on all of that, we picked off the numbers of sensors that we needed and placed them intelligently. So it was a network design problem, and we examined what sort of design efficiency we wanted, what sort of detection limit we wanted, but could intelligently design how many sensors we put out, of what type, and where we put them, given the constraint, the physical constraints of where you put the sensors. So then we went out and built this. We built it in a couple of different ways. One way that we built it was to have relatively inexpensive sensors out. So large numbers of relatively inexpensive sensors. That's one solution to the design problem. Another way to solve the design problem is to pick relatively more expensive sensors, and not surprisingly, the sensors that give you the better precision are more expensive. But which is better, a sparse network of really accurate sensors or a much denser network of less precise sensors? So we deployed both. And we began operating the network. We've been operating this phase of Project Astra since early 2022. We're continuing to run it. The system will be uninterrupted through the DOE funding, which has now begun, and we're going to continue to operate the network. What we're going to do as well, though, is do some expansions that I'll touch on in a moment, but let me tell you a little bit about some of the key findings, and you can see these out in the posters, and see more technical discussions of these out in the posters. But first, how do we define a detection? So you're getting this continuous signal. What constitutes an event detection? How much of a methane enhancement do you need to see? Or should you be looking at the rate of change of the methane concentration? Or should you be putting in a persistence criterion? What defines an event? All right? That's a challenging problem. And so we've been looking at that systematically. We've also been collecting a lot more data on data capture. How long are the sensors up? What sort of downtime do we have? And then what challenges do we have with interferences and background concentrations and so on? We've also then been looking at the policy interface. So for example, we have a number of preprints that we put out saying, all right, if you put out a continuous monitoring network with one sensor per site, can you demonstrate an equivalence like Arvind talked about with the Phae modeling? Can you demonstrate an equivalence with optical gas imaging deployed once a quarter? If so, how many times do you need to respond? Do you respond every time the sensors go above 1 ppm? All right, or do you put in different thresholds for your response to the system and going out and investigating? So we looked at those issues as well. We're continuing to work on our modeling and evaluating the dispersion models, looking at how we can get data on event duration and practices for event duration. So a lot of this is described out in the posters. What we'll be doing with the Department of Energy funding is several things. So look forward to this over the coming years. One is to look a lot more at quantification. So taking the concentrations that we observe, really evaluating our dispersion modeling, and defining what our uncertainties are in emission quantification. Then in addition, the 50-site network that we currently have deployed is really focused primarily on production facilities. We're going to be expanding it to gas processing facilities and gathering and boosting stations and collecting a lot more data on those more complex sites, which as Dorrit pointed out, we expect to present a number of additional challenges with us. So that's a quick overview of how we've progressed through doing continuous monitoring systems. And so I'm going to stop there.